Welcome back to the course on statistical mechanics of phases and phase transitions. Today we are going to start a new chapter on the Ising model and in particular the Monte Carlo method. So it's a good idea to start by reviewing the course so far. So we started off by discussing physically motivated models. We tried to solve them at least approximately. The interacting gas model we were able to successfully solve approximately. And the idea is to solve these models, obtain a free energy, and then study the free energy for non-analyticities and obtain information about phases and phase transitions. As I said, we have done this for the liquid gas transition, and we have even computed the critical exponents for these. They turned out to be close to the experimental value, but not quite matching the experiments. So what are we going to do in the new chapter that we have just started today? So the idea is we'll focus on the Ising model, and we will study the Ising model in various dimensions. Now you will see that the Ising model is a difficult model to solve, especially in higher dimensions, and so you will see that the tricks of trying to find some small parameter etc. will not be very successful. So what we will do is, before we delve into the analytical approaches to the Ising model, we will learn a numerical method to solve the Ising model called the Monte Carlo method. What this will allow us to do is, it will allow us to prepare a program, a computer program, before we start the analytical study, so that we can use the Monte Carlo program that we will develop and check the analytical results. We can sort of make a side-by-side comparison of variety of things, and it will allow us to learn more about the Ising model and how the physics of interactions etc. play out in this model, and this is what our plan is. So the strategy is the following. We will focus on the Ising model. As I said, we can only solve the Ising model approximately, even only in certain limits. Particularly, we will see that we can always do it in the very high temperature limit and very low temperature limit. But in particular, if there are phase transition, it's difficult to tackle the Ising model there. So reliable analytical solutions are not available, and the strategy is, we'll learn how to solve the Ising model on the computer using the Monte Carlo method, and we write our own program, use the program to check and understand the approximate results that we'll be deriving later. And most importantly, you can use this program to ask and answer your own questions. So I'm going to introduce the Monte Carlo method first, and I will sort of be focused on the Ising model, but I must emphasize that the ideas that we are developing here are widely applicable, and it's not just for the Ising model. You can easily generalize it to study more many interesting models. Okay, so let's start with the Ising model on a d cubic lattice arena. So I have n sites, and you can think of n as some L tilde to the d, so it's like a cube of side L tilde in units of lattice spacing with periodic boundary conditions, right? So the configurations of the spin is that you define a spin variable at every site, and that will tell you the configuration, one of the spin configurations. And the energy associated with the spin configuration has this interaction term. So this we will, for starters, keep it to be nearest neighbor interactions on the links, and this is described by a scale j, which is the exchange constant. And then if necessary, we can even add an inhomogeneous field. This is an external field you can add, and we can use this to study variety of things. In the beginning part of our discussion, we will not use any field, but we will just use the Ising model, and maybe as an exercise you can add fields and you can study the problem yourself. So generically, we will be interested in some observable which depends on the spin configuration. It could be magnetization, it could be some spin fluctuation, whatnot. It could be a variety of observables, and you can get the expectation value observable by summing over all the probabilities of the configuration C, and the probability of the configuration C, as we know from the canonical ensemble, is given by the expression that I am pointing to here. Now you might think that, okay, if I start with some small system, maybe I say I take a square lattice with 10 by 10 sites, so I have 100 sites. You will see that summing over all the 2 to the n configurations by hand is prohibitively impossible. And so even for realistic systems, you know, if you consider systems that are required to get thermodynamic information, it's impossible to do this sum exactly. So what would be a strategy to attack this problem? And this is what will land us into Monte Carlo territory. Okay. So the idea of Monte Carlo is to sort of gamble in a sense. The key idea is to not to sum over all the configurations C, but rather visit the most important configurations. Now, what do I mean by most important configurations? The most important configurations are the ones that have a high probability, in the sense that this rho of C is large. But this is a bit problematic, because to find rho of C, it's not enough to know the energy of C, which is h of C, but you also need to know the partition function. But we cannot evaluate the partition function because the problem is too large, too big. So what is the idea of Monte Carlo method is to start with some configuration C1, right? You start, so what I'm plotting here schematically, imagine this axis C that I'm drawing here is the space of configurations. Please mind that this is not any arena or anything like that. This is the space of configurations. It's schematically represented as a line here. So this is one spin configuration, this is another spin configuration, etc. So what we are going to do is we are going to start with a configuration C1, let's say here, and then we want to find a way to walk in the configuration space. We want to step to another configuration by comparing what is rho C1 and rho C2, and you continue on, and the crude idea would be that if this is the probability distribution which I have schematically represented here, as you do this walking around, most of the time of this walk will be spent in the regions where the probabilities are higher, such as this set of configurations and this set of configurations, etc. These set of configurations which I am pointing to by the pointer here and here, for example, the system as I am walking around will spend as little time there as possible. Remember, this time is not real physical time, it's the time that I am using to step. So this is the idea of what is called as importance sampling. So what we want to do is we want to develop a method for importance sampling the configurations. So we need an algorithm to take these steps. Okay. So this algorithm requires a certain kind of dynamics, in the sense that you need to tell me if I am in a certain configuration, how will I go to the next configuration. So for example, if I am at C3, I am showing here that I have jumped to C4. How did I decide to jump? I need this sort of dynamics. Okay. So I am going to introduce the idea of Markov chains, and what I will do is, we are interested in the probability rho of C, which is the equilibrium Gibbs probability distribution function. But for the formulation of this problem, I need a more general probability distribution, which I am going to call as P of C. P may be different from rho. In fact, when we start our simulation, P may not even be anywhere close to rho. It has to evolve to rho, as you will see. And this is defined over the configuration space. So the idea is that we are positing that there is a probability distribution over the space of configurations. Okay, to simplify the notation, I am going to say that the configurations there will be nc of them, script nc of them, which is in the Ising problem is 2 to the power number of sites, and we'll just call them as C1, C2 all the way up to C and C. We find some way of numbering these, and they are all numbered, let's say, in this way. And what we will say is that we will say that the probability of configuration C1 is P1 and probability of configuration Cm is Pm and so on, and we will simply use 1, 2, 3 to talk about the configurations themselves and just drop the script C notation for the configuration. This will simplify our equations, at least the appearance, it will not be very heavy on your eyes. Okay. So the first thing that we want to think about in a Monte Carlo is the notion of a step. So you can think of this step like some kind of clock tick. So for example, in music we have this tala. So there is a tick, there is a regular tick that is going on, and remember that this should not be thought of as some physical time. This is some walk we are designing into the configuration space, and the rule is that every time I have a hit or the clock ticks, I have to make a jump to another configuration. So the idea is that at every tick, the system will make some kind of transition from one state to the other. So this is what I call make transition from M to N. So if you accumulate the number of steps that we have taken, the number of times the clock has ticked over a period of time, that will give us what is called as a Monte Carlo time, which I will denote by T. Remember again, I want to emphasize this is not physical time. It is the time of the simulation, if you wish. This time steps that we have taken in our calculation. And remember, this is a discrete time. It's just a number of times that you have changed your configuration. So the question we want to ask is the following. Suppose we know that the system is in some configuration M at time t. Where will it be in time t plus 1? So it will certainly transition to some other state, probably N, but which one should it be? So what we are going to postulate is that this transition is going to be determined by something called as a transition matrix, which I am going to call as WNM. So it tells you what is the probability that if I am in a state M, that I will land up in a state N in going from time step t to time step t plus 1. Okay. So pictorial way of showing this is that this is the set space of configurations. I have just numbered it from 1 to NC, and let's say I am in state M. Then in time t plus 1, the probability that I will land up in state 1 is W1 comma M. The probability that I will land up in state N is Wn comma M, and the probability that I will land up in state land up in the state NC is Wnc comma M. So what is this W matrix? The W matrix is a massively big matrix which is NC cross NC. So it is 2 power n by 2 power n matrix with these components. So this might look a little daunting, but let's proceed and see where we can get with this. So in general, such a process where some set of objects start and there is a rule for making transitions to other states, and in general this matrix can even be dependent on the time, such processes are called stochastic processes. And this is a very important and well studied subject that has applications in many areas of physics, engineering and all of science actually. We will need a set of stochastic processes which are called as Markov chains. So let's see what Markov chains are. In a Markov process, the probability of going from M to N at a given time does not depend on how the particle or how the system, I should not say particle, how the system reaches the configuration M at time t. So it has a history. A Markov process does not remember history. This process is in a sense homogeneous in time. If you take that the process is homogeneous in time, what I mean by that is that this WNM does not depend on time. That is, if for all times t, this WNM matrix is the same. Then you will see that this Markov process, this process will be a Markov process. Now, we have postulated the existence of this transition matrix, and we have said that the transition matrix does not have any memory, and it's a Markov process. Now, if you see, I am in the state m at time t, and WNM is the probability that I will transition to the state n. Now, if I sum over all the possible states that I can realize, which are NC of them, you will see that this has to sum to 1, because that is the sum of probabilities. And of course, each probability has to be greater than or equal to 0. That is just the fact that it is a probability, and therefore it should be a non-negative number. Okay. So, with this information, I welcome you to explore this point, that if I have this very large NC by NC matrix W with these conditions, you have to show that every right eigenvalue of this has magnitude less than or equal to 1. It is a very simple exercise, but worth doing. Okay. Now, suppose at time t that the probability of realizing the configuration Cm, which we have simplified as with the notation m, is Pm comma t. So, what am I now doing? I have this Markov matrix. I am now thinking that the system has some probability distribution of being in certain configurations, and that is what I am going to call as Pm of t. Okay. So, the system now at time t has some probability that will be in P1, that is P1t, and Pm will be Pmt, and so on. So, what I can do, that the probability distribution at time t can be thought of as a column vector. So, what is this column vector? The column vector will have all these P1, P2, P2t, Pt3, and so on. It will become a column vector, and that is what we indicate by this matrix Pt. So, it is an NC by 1 column vector. So, the question we are going to ask is the following. Given a Markov matrix, which we have just discussed in the last slide, and the knowledge that this probability distribution of the configuration space at time t is P of t, what is the probability at time t plus 1? So, how does a probability distribution at a given time evolve by a Markov process, by a Markov matrix? So, it turns out that it is actually very straightforward to calculate. So, you will see that Pn of Tn plus 1 is whatever was the probability of state m, that just gets added up at to state m by this weight, and you can see that it will just go to Pt, and Pt plus 1 is simply the matrix W acting on P of t. Okay. It is a very simple idea. But you can ask, how does the probability change with time? Okay, so I have to take the difference of Pn of t plus 1 minus Pn of t, and so Pn of t plus 1 is just this, it is just W times P of t. Now, I play a small trick here. What I am going to do is, I am going to take this Pn of t, think that there is a coefficient 1 here, and remember the sum over all m of W mn is 1. So, I will end up getting this very nice result. And what I am getting is, I will get that this statement here, Pn of t minus Pn of t plus 1 minus Pn of t is this result. This equation is called as the master equation. So, once I have the master equation, I have immediately a very nice result, that if I have a steady probability distribution. Now, what do I mean by a steady probability distribution? A probability distribution that does not change with time. So, that means that I need the left hand side of this equation to be set to 0. So, I have a steady probability distribution will imply that since this quantity is 1, it will tell me that W of P, W acting on P as a column vector will turn out to be P itself. What does this mean? This means that a steady probability distribution is a right eigenvector of the transition matrix W with eigenvalue 1. So you can imagine that there is an eigenvalue 1 here, and that is the statement that the steady state distribution of a Markov process is given by a probability distribution which is the right eigenvector of the Markov matrix with eigenvalue 1. Okay, and that is the statement that is highlighted here. Okay, so this is already very interesting. I need to look for steady states of Markov matrices. So what will be our strategy to walk in the space of make a walk in the configuration space that will sample my probability distribution according to the Gibbs weights of each of these configurations. So our statistical probability distribution is the Gibbs distribution, rho of C. And we now collect this Gibbs distribution in a matrix, which is what is indicated here by this sort of double font row. So what our strategy is, we want to construct a Markov matrix W such that rho is a right eigenvector of W with unit eigenvalue. So this is a little strange, because in our studies usually we are given the matrix and we are asked to compute eigenvectors and eigenvalues. Here I am giving you the eigenvector and the eigenvalue and asking you to find the matrix. So this runs into several issues. So the first thing is that there may be many matrices for which rho is the right eigenvector. Right? You can just write just think of a column vector with 2 entries and ask how many matrices are there for which that column vector is an eigenvector. You can easily find many matrices. You can just check it yourself. So the first point is that this question of what is W for which rho is the right eigenvector with unit eigenvalue may not have a unique answer. Second, even if we find W rho is a W for which W rho is rho, we cannot ensure that rho is the only right eigenvector with eigenvalue 1. Because if there is another eigenvector with eigenvalue 1, then then that could also be a steady state, and then we would that probability distribution may be a different distribution from the Gibbs distribution that we want, and we may run into trouble. So what we would like to do is we would like to see how can we ensure that the W matrix that we construct has only one eigenvector with eigenvalue 1. Okay. To answer this question, we need to study a little bit more about Markov process. Okay. So this is the question. Let me remind you, we need to construct a Markov matrix W for which our rho, the Gibbs distribution, is the only right eigenvector with unit eigenvalue. So I will show you in a bit that we are going to use a key theorem of Markov processes to achieve this. So we need a few concepts to understand the theorem itself, and those concepts are extremely crucial for us to construct a sound Monte Carlo algorithm. So even if we are not going to be formally detailed about this, we will certainly want to understand the conceptual foundation of these ideas. The first idea that we need is the notion of an irreducible chain. We have to also understand the idea of recurrent states and positive recurrent states. We have to understand what do we mean by an ergodic chain, and we have to also visit the notion of aperiodic chains. Okay. So the first thing we would like to discuss is the notion of a visit probability. To see what these ideas mean, we have to introduce the idea of what we mean by a visit probability. So the notation for this is Vn, n t. So this is the statement that the system, what is the probability that the system reaches n at time t if you start with m. Okay. So you can, of course, you can try to work out what is this v of t in terms of w. I invite you to do that. And the quantity Vnm is the sum over all times. So this will go to all the way to infinity of Vnmt. So what will this quantity Vnm tell you? It tells you what is the probability of going from m to n at some time. Okay, so this is the total visit probability of n from m. Okay, so now we are ready to define what is an irreducible Markov chain. If Vnm is non-zero, that is, I can visit any configuration from any other configuration. It may take a long time to do that, it does not matter. If it is finite, if the visit probability of n from m is finite for all n and all m, then we say that the Markov chain is irreducible. So roughly speaking, it is not that what would be a reducible Markov chain. So that means that there are a set of configurations and another set of configurations. So if you start from this, let us say this configuration set A, if you start from some set of those configurations, you will just remain, as you walk around, you will be just remaining in those A configurations, and these configurations remain in B configurations, and B will never go to A and A will never go to B. Such a process is a reducible Markov process. So if the visit probability between any two configurations n and m is non-zero, then we say that the process is irreducible, and this is an important and critical concept, and it will turn out to be the main thing that we have to ensure. Okay. All right. A state is called recurrent if Vmm is 1. That means that it comes back to itself. That is, particle can come back to itself. It is called positive recurrent if sort of the average time it takes to come back is finite, right? And this is what we call positive recurrent. And if all states in your system are positive recurrent, then we say that the system is ergodic, in the sense that an ergodic system is you start a Markov process at some configuration m, you are certain that after some time you will be back at m. That is roughly what it means. Alright, we need one more concept, which is the concept of an aperiodic Markov process. So the idea here is that no state, no configuration repeats itself periodically. So for example, there is no m such that after every 20 steps you will be back at m. So this is an important necessity as well for what I am going to present soon. So with these ideas put together, we can now state the fundamental theorem of irreducible Markov chains. We will certainly not attempt to prove it, right? The statement of the theorem is an ergodic aperiodic irreducible Markov chain has a unique stationary probability distribution. So if a chain satisfies the condition of irreducibility, aperiodicity and ergodicity, then the stationary state, namely the probability distribution which is the right eigenvector of the Markov matrix with unit eigenvalue, is unique. So if we are able to design a W which is irreducible, ergodic and aperiodic starting from our Gibbs distribution, then we are certain that the Gibbs distribution will be the only one which is the steady distribution of the Markov matrix that we are constructing. So what is the most important thing to ensure, it turns out, in the Monte Carlo methods that we will design particularly for the Ising model, let us say, on the computer, is irreducibility. What do we mean by irreducibility? I will just recall that. Irreducible means from any configuration I should be able to reach any other configuration by my stepping process. There should be no restriction that a certain configuration cannot be reached from my configuration by my stepping algorithm. Okay. The other conditions turn out to be fairly easy to implement, because however large we are our system may be, they are still finite and so on. So the other things can be easily implemented. So the most important thing is irreducibility. Okay. So what is it that we have done in this lecture? Let's try to summarize. So the key points of this lecture are: 1, we aim to explore the Ising model, and there is no obvious small parameter to analyze the Ising model analytically, particularly near phase transitions, which we will see later in the course. So what we decided to do was, we decided to prepare ourselves with a numerical tool, so that as we encounter different approximate analytical results, we will be able to go to the computer and we will be able to check and understand our analytical results and compare how well they are doing and whatnot. So the idea of the Monte Carlo method, which is going to be the numerical workhorse, is to perform a walk in the space of configurations that will sample the most important configurations, namely those configurations which have the highest probability. So this is done by designing something called a transition matrix or Markov matrix, and the right eigenvector of this transition matrix will be, we want to design the Markov matrix in such a way that the right eigenvector given by our Gibbs distribution rho is the one with unit eigenvalue, therefore a steady distribution of W. To do this, we invested some time in understanding what is the fundamental theorem of Markov processes, and what's coming up in the next lecture is that we will use this theorem to develop a Monte Carlo method for the Ising model. So I am sure with all the exciting things we have seen in this lecture, you will join me for the next lecture. I will see you then. Thank you.